Welcome back, students. In this video segment, we will cover one section, section 4.3, the law of cosines. We're going to finish up in this section our discussion of oblique triangles. We might as well start with some good news. There's a couple of bits of good news with this section. First, the section's pretty small, or pretty short, so we'll be through this video probably in not too long. It won't be another hour and a half video. And there's some other good news about this law coming up soon. So let's get started. Okay, first, recall that the law of sines is used to solve three specific cases. Cases where you're given a side and two angles, side, angle, angle, but the side is not between the two angles. And the next case is angle, side, angle, where you're given two angles again, but the side this time is between those two angles. And the case we have to be really careful with, the side angle case, where there's a possibility that you'll have no solutions, and there's also a possibility that you'll have two solutions, two triangles form. Okay, so good news. Second bit of good news. There is no tricky two triangle case. I can't say that real quickly. There's no tricky two triangle case for the law of cosines. So when we have a solution for the law of cosines, there will only be one. There will only be one. There's only one little cautionary note. This one is seems a little strange, or it might seem a little strange, but it's not complicated. If you start a problem with the law of sines or with the law of cosines, don't switch methods in the middle of solving the problem, or at any point solving the problem. Which means that if you're using the law of sines, if you start with the law of sines, don't switch to the law of cosines to find pieces of information about the triangle. Stick with the law of sines. And conversely, if you start with the law of cosines, don't switch partway to the law of sines. The details of the reason for this I'm not going to go into, it's not really instructive, but basically, if you start with the law of cosines and switch midway to the law of sines, you could find yourself in the case using the side angle, involving side angle, but the information that you're given won't indicate that you're finding the wrong triangle. I don't think that came out right. Basically, if you start with the law of cosines, you could end up and switch to the law of sines. You could end up in the case of the law of sines where you have the second of the two triangles possible, but you won't know that you found the wrong triangle. You will solve the first triangle case. So see, it's not really easy to put in words in a simple way. The best thing is, if you start with a particular law, stick with that law until the end, even though if you start with the law of cosines, it might seem easier to use the law of sines to find some information. So if you start with the law of sines, end with the law of sines, stick with the law of sines, and conversely, if you start with the law of cosines, stick with the law of cosines. Okay, so we need to do a couple of things. First, we need to discuss what the law of cosines looks like. Then we need to solve two pretty simple, straightforward examples, okay? So, the easiest way to describe the law of cosines without writing it out, or to start describing the law of cosines, is that it is nothing more than a generalization of the Pythagorean theorem. Let me explain. So let me draw a right triangle here first. So here's a right triangle. Even though our section is involving oblique triangles, we're going to start with a right triangle. So here's my right triangle. Okay, so let's label the angles on the sides. So let's call this angle B, lower left, angle A above, C we'll call the right angle. So once we do that, we're going to use our convention of sides, saying that if the lower left is B, then the opposite will be leg B, leg of length B, angle C, hypotenuse small c, angle above A, opposite that the horizontal side, small a. Okay, so the Pythagorean theorem says c squared equals a squared plus b squared. This is not news, shouldn't be news to you. You saw this before you took geometry. Now, let's take a look at the law of cosines. The law of cosines, again, doesn't have the special two triangle case. There's a little bit of a, not so much of a trade-off, but there's a little bit of an aspect of the law of cosines that makes it a little more intense than the law of sines, and that's that the formula for the law of cosines is a little more complicated. So let's take a look at that formula. I'm going to draw an oblique triangle. I'm going to take the angle C in the right triangle that I've just pictured there, and I'm going to make an oblique triangle. So let's get rid of that right angle. So there's the lower side. There goes that right angle, all gone. And let's take a look at, well, we don't have hypotenuse anymore because this is not a right triangle. So let's just call it the longer side. I'm going to or not relabel, but I'm going to label this triangle the same way as I did above. Oops. C, B, A. So clearly, the Pythagorean theorem does not hold here because we don't have the right angle any longer. However, the law of cosines just generalizes the Pythagorean theorem. So the law of cosines looks like this. There are actually three equations for the law of cosines, but all three of them work just the way I'm going to write this one. The Pythagorean theorem started out with c squared, and on the right-hand side it has 8 squared plus b squared. So the law of cosines also has this as a beginning. However, on the right-hand side, we have to subtract 2 times a times b times the cosine of the angle C. Okay? You see what I mean by we have a little bit of a extension in difficulty, a little increase in difficulty in how the formula. It looks a little more complicated. It's formed in a little more complicated way. But really, if you can memorize the pattern of the law of cosines rather than the specific law of cosines with the variables c, a, and b, then it's very, very simple. Okay, so let's take a look at how this pattern, or what this pattern is. Well, notice that we start with small c on the left, and we end with the angle opposite that's capital C on the right. And then we also on the right have the usual version of the Pythagorean theorem. So c squared equals the sum of the squares of the other two, a squared plus b squared. Then we have that complicated minus 2ab cosine c. But notice that the 2ab is just a repeat of the variables a and b. Okay, so we start with small c, we end with capital C. The first two terms on the right are like the Pythagorean theorem, a squared plus b squared, but then you subtract 2 times a times b times the cosine of the angle C. So if you didn't notice a pattern, I think you're going to when I show you the other two versions of the law of cosines. There are two other versions. One of them is going to start with b squared on the left. So what do you suppose the form of the law of cosines that starts with b squared on the left ends with on the right-hand side? Well, if the first version I gave you, C started with small c squared and ended with capital C, then it seems logical that the second version that starts with b squared should end with cosine of b. Filling in the rest is very simple. B squared equals the sum of the squares of the other two variables, so a squared plus c squared. And then minus 2 times a times c times the cosine of b. So let's see if you can follow with me on the last version of the law of cosines. So the last version of the law of cosines starts with a squared. So a squared should equal b squared plus c squared minus 2 times what times what? Well, look above. B squared equals a squared plus c squared minus 2ac. A squared then equals b squared plus c squared minus 2bc times the cosine of what? We started out with small a. We finish with capital A then. So we should finish with capital A. Okay, so the pattern is very, very simple to remember. Here's a sort of self-test for you. Let me draw another little triangle here. Give me a second. I'm going to draw a triangle here, and I'm going to label that triangle with different variables than A, B, or C. Shouldn't matter. So here we go. Let's say we call this angle here theta. And this side opposite theta is x. And maybe the horizontal side y and the longer side z. So let's write out a version of the law of cosines involving x, theta, y, and z. So we start out with x squared. Just like before, we started out with a squared and ended with cosine of the angle opposite a. We started with a squared. We started with a squared and ended with the cosine of the angle opposite a. So we're going to start with x squared and end with the cosine of the angle opposite x. So x squared equals y squared plus z squared. There's no other things to put in besides except for y squared plus z squared. There's no other two variables to add the squares of. Okay, so minus 2 times what times what? 2 times y times z times the cosine of theta. It's always formed this way. The law of cosines is always formed this way. If you don't see the pattern, I think you ought to maybe consider going back in the video, maybe 3 to 5 minutes, and look for that pattern again. It will be well worth your time. There's really not much to memorize with the law of cosines. So I promised you a shorter video, so let's take a look at 2 examples to finish things up. Example. Solve the triangle. Let's say solve the triangle or triangles if possible. Now this is going to be a law of cosines example, so there's only going to be one triangle, and yes, it's going to be possible. However, I want to prepare you for your exam by allowing the possibility that this could be the special 2 triangle case for the law of sines. Because on your exam, you're not going to be told, hey, this is the law of cosines case, go ahead and do it. You have to decide first, is this a law of sines or law of cosines? And if it's a law of sines, is there a possibility that I might have that 2 triangle case? So just to prepare you for that. So A of 2 parts, A and B. So B is 45 degrees. Let's see. Let me make sure I got these right. C, small c, is, let's say, 6 or 6.0. And what else? B, small b, is 9.0. Okay, so let's do this. First thing we need to do is draw the triangle and decide what case we have going on here. Remember to prepare yourself for the possibility of having the 2 triangle case of the law of sines, we always try to draw our triangle the same way. That is, if we have an angle, and we do have an angle here, let's put it in the lower left-hand corner. Okay, so here's 45 degrees. So obviously that's B. Now we're given B. No, I guess I should. Oops. We're given B. So here is side B. We're also given side B. We'd like to leave the side that's horizontal blank. Okay, again, this is just to prepare us for the two triangle case of the law of sines. So it would be probably the best idea to call this side above, or this angle above, is actually correction. It probably would be a good idea and I owe you an apology. I mislabeled the given information, so I'm sorry. This is going to be an easy fix, though. Sorry, guys. So I'm not going to do it off camera. I'm going to do it on camera so you see this fix. We're given that A is 9. So A is 9. Okay, so let me get rid of that B over there. B is not known to us. And I knew that was going to be a problem. Okay, so try to leave the horizontal side blank. So that means we need to put C next to B, the side C next to B, and side C, which is correctly labeled as 6.0. Well, we can't put anything opposite B because we're not given B. Now we're forced to put as that horizontal side A, which is just fine. It's just fine. Try to leave the horizontal side blank. If you can't, then this is good news, and this is not going to be the case side-side angle. Okay, since I labeled 6.0 as C, then the angle opposite of that should be capital C. Okay, so we're all fixed up here. So again, I apologize for the glitch there. So I want to go after B. I want to go after the angle or the side small b. So I'm going to use the version of the law of cosines that starts with B. Well, why are we using the law of cosines? Well, what case is this? Side. Two sides are given, and the angle between them is also given. Okay, so why should this not be the law of sines? Because the law of sines says that we have the case side-side angle. So remember, law of sines was side angle, angle side angle, and side angle. And side angle side is not one of those. So the law of cosines handles the only two remaining cases, the side angle side, which is our case, our current case, or side. Okay, there is no case angle because it's impossible to solve for a triangle if you're given three angles. So we're in the case side angle side. So we're going to use the law of cosines. And the law of cosines that we're going to use, the version of it, starts with side small b, so b squared. So do you remember what we're going to end with on the right-hand side? We're going to end with the cosine of what? Angle b. So b squared equals, if you missed that, don't worry about it, b squared equals a squared plus c squared minus 2 times a times c times the cosine of the angle opposite small b, which would be capital B. Okay, so let's do this. So b squared equals a squared, 9 squared, I'll leave the point O's off, plus c squared, 6 squared, minus 2 times 9 times 6 times the cosine of the angle B. So it's really very simple to enter the information once you have the version of the law of cosines decided on. Okay. Now you can do the computation for B in one long step on your calculator. So if you solve for B, that is, if you take the positive square root of both sides, then you can enter this in one step on your calculator, minimizing the chances for errors in entering. Okay. So first thing you would do in your calculator is turn it on, of course. Then put it in the degree mode. Make sure your calculator's in the degree mode when we're solving these triangles. Then what you would do in your calculator, let's do this as a calculator computation. Calculator is you would push the square root button. When you push the square root button, it opens the calculator opens the parentheses for you. It'll be waiting for you to enter the computation. If you have a newer version of the TI-84, then there's no need to worry about parentheses at all. Your calculator, as long as you don't push the right button and get out of the radical, your calculator will extend the radical sign through your whole computation. Then you enter it just the way you see it. You push 9 and then the x squared button. So you push 9 and the x squared button plus 6 and the x squared button, 6 and then the x squared button, okay, minus 2 times 9 times 6. And you can either push multiplication or not. Your calculator, if you just push the cosine button, will know. So if you would push 9 squared plus 6 squared minus 2 times 9 times 6 cosine of 45, then close your parentheses. So push cosine of 45, cosine button, 45, and then close your parentheses and push enter. And your calculator will compute this for you. Your calculator will compute this in one fell swoop. So if you do this computation, maybe round to 1 decimal place of accuracy, you have B is approximately 6.4. My calculator gave me 6.37436, etc., etc., etc. So about 6.4. Okay. Okay, so here's the deal. We need to hunt for an angle. We need to look for an angle here. So remember what I said. When you start with a particular law, in this case the law of cosines, don't switch to the law of sines midway through, even though the law of sines would definitely be easier to look for an angle. It could be disastrous, okay? So just, we're stuck with the law of cosines. So let's hunt for the angle C. So to hunt for the angle C, I'm going to start with the law of cosines. It starts with small c. So c squared equals a squared plus b squared minus 2ab times the cosine of c. And I'm going to solve this equation for the cosine of c. Okay, a little bit of algebra involved here. So I'm going to add 2ab times the cosine of c to both sides. So I'm going to get I'm going to add 2ab times the cosine of capital C to both sides. So I get it on the left-hand side and positive. Then I'm going to have a squared plus b squared still left on the right-hand side, and I'm also going to subtract small c squared from both sides. Then I'm going to divide both sides by 2ab. So the cosine of c equals a squared plus b squared minus c squared over 2ab. Okay. So at this point, I'll have the cosine of c, but I'm looking for c. At this point, the formula says the cosine of c equals, but I'm looking for, not for cosine of c, I'm looking for c. So what would be the last operation I use in my calculator to go from cosine of c to c? Would it be the cosine function? No. What would it be? would be the inverse cosine. So the formula for the angle C, let's see if I make my angle a little bigger. Cosine formula for the angle C here equals the inverse cosine of all that stuff on the right, a squared plus b squared minus c squared over 2ab. Okay, so back to our problem. Our problem had b is 45, c is 6, a is 9. Right, let me move that down here. Okay, so I moved our information from above, including the b that we found. So let's put that into the formula for c. So c equals the inverse cosine of a squared, 9 squared. That doesn't look like a 9, it looks like an a, doesn't it? 9 squared plus b squared. So I'm using the approximate value for b. You want to increase the accuracy a little bit, use more decimal places of b. So 6.4 squared, I'll just use the approximation, minus 6 squared all over 2 times a. A is 9 times approximate 6.4. Okay, when you find that, and you do this, you push enter in your calculator and you get a really good approximation, pretty good even with the rounded off 6.4 for b. We get about 42 degrees, 41.7 or 42 degrees approximately. So in your graphing calculator, to enter the inverse cosine, just to remind you, you push second cosine. And if you're going to do this in one step, which I totally recommend, you're going to need to insert parentheses. So you would insert parentheses. When you push inverse cosine, the calculator will open the parentheses for you. So the open parentheses on the left-hand side is what you would enter. Then you would enter 9 squared plus 6.4 squared minus 6 squared. You would close you have to do this. You close the parentheses for the numerator, then divided by, then open the parentheses for the denominator, close the parentheses for denominator, and close the parentheses for the inverse cosine. So I'll put this in red and push enter. So you would enter inverse cosine and the calculator would open the parentheses for you. Then you would insert parentheses and push 9, the x squared button, plus 6.4, the x squared button, minus 6 squared. Close the parentheses, divided by, open parentheses, 2 times 9 times 6.4. Close the parentheses. Close the parentheses for the inverse cosine. The calculator will open the parentheses for you in the beginning, and then press enter. So you should play around with that. It's not rough at all. You'll become a champ at this really quickly. So we found C is approximately 42. So I'm going to go up to my triangle. I'm going to put in the stuff we found. So C is approximately 42 rather. B is approximately 6.4. The only thing left is to find angle A. I would not recommend you use the law of cosines for it. It's very simple to find A without using any special law for trigonometry. Just use A equals, since the angles have to add up to 180 in every triangle, A is 180 minus 45 degrees, approximately minus 42 degrees. I say approximately because C was an approximation. So A is about 93 degrees. I'll keep it in green, why not? And we've solved the triangle. Okay. So the only other thing I'm going to do for you is one more example. I think it'll go fairly quickly. I wanted to solve an example with the very last case, side, side, side. I'm given three sides. Let's say A equals 5, B equals 7, C equals 10. Okay. So for this particular case, there's not too much of a worry about having the law of sines case where you have two triangles, primarily because there's no angle given. Okay, so it can't be side angle. So just draw a triangle, and we'll fill in the missing pieces of information. So I'm given the smallest side is 5, so I'll put that in the smallest position. Medium size side is 7, longest side is 10. So that longest side was C, so opposite that is capital C angle as the angle, and 5 was the small a, capital A, opposite that. Small b7, capital B, opposite that. So we need to find these three angles. Okay, so I'm gonna find A and B, and then find C is just 180 minus those two things. I'm going to find A and B using the law of cosines. So I'm going to start out with the form of the law of cosines. It started out with A squared. So A squared equals B squared plus C squared minus 2 times B times C times the cosine of what? A squared equals B squared plus C squared minus 2BC times cosine of A. I'm going to solve that formula for A. Now, some of my students over the years have told me that they just memorize the formulas for the angles A, B, and C. For me, it's so simple just to derive them every time I need them. So I just start out with the law of cosines and solve for A, for whatever angle I need. So just as before, the cosine of A equals B squared plus C squared minus A squared over 2BC. Nobody's ever died as far as I can tell from doing too much algebra. Don't quote me on that. Okay, so the last thing we do is we take the inverse cosine, so we might as well have a complete formula. So A is the inverse cosine of B squared plus C squared minus A squared over 2BC. With our calculator, of course, in the degree mode. So let's find the angle A. Let's find the angle A. So the angle A is the inverse cosine of B squared plus C squared. B was 7. C was 10. So 7 squared plus 10 squared minus A squared. A was 5. Oops. 5 over 2 times B times C over 2 times 7 times 10. We do this in one fell swoop in our calculator by inserting parentheses in numerator and denominator. Just make sure we do that. We got to do that. Okay, and we get A then is approximately 27.666, so it's about 28 degrees. Okay, I'm going to do the same thing with B. I want the angle B. B squared equals A squared plus C squared. I'm starting out with the version of the law of cosines that starts with B. So B squared equals A squared plus C squared minus 2 times what times what? Minus 2 times A times C. Cosine of the thing I'm looking for, cosine of B. Use some algebra to solve for B. So I'm going to get that 2AC cosine of B on the left. I'm going to add it to both sides. I'm going to have that A squared plus C squared on the right, and I'm going to subtract small b squared to try to isolate further B, capital B. I'm going to divide by 2 times A times C. A squared plus C squared minus B squared over 2AC. And the last thing I would do in my calculator would be to take the inverse cosine. So I'm going to have A squared plus C squared minus B squared over 2ac. So let's do this. Let's find b. b should equal the inverse cosine of a squared plus c squared, so 5 squared plus 10 squared. I think that was a and c. 5 squared plus 10 squared. Good. 5 squared plus 10 squared minus b squared minus 7 squared over 2 times 5 times 10, 2 times a times c. Calculator tells me, remember, insert parentheses in numerator when you're computing numerator or entering numerator and denominator in your calculator. My calculator will tell me that b is about 40.53, etc., etc., so about 41. There's not much left to do. The only thing I need is angle C. Angle C, then, is 180 minus the b that I found, minus 41, minus the a that I found, which was what, 28 degrees. So C is approximately equal to 111 degrees, and I have all three angles for my triangle. And that ends the triangle. Not only does it end the triangle, it ends this video segment. So go ahead and confidently dig into section 4.3, the law of cosines, knowing that you're not going to get any of those pesky two triangle cases. And as usual, I am looking forward to talking with you again soon.